In this video, let me show you how to answer the question and explain the theory also behind how we calculate the acceleration of this, right? Of this mass that's falling in our laboratory, pulling that tape through it, right? Now, ideally, we think, obviously, that it should be 9.81 meters per second squared, right? Or 981 centimeters per second squared, right? But it's never going to be that high, and we're not going to get the same number a whole bunch of different ways. And as far as which one's the better way to do it, I just don't know. But we'll cross that bridge when we get to it in internal assessment. Okay. Now the first way is to do it from the polynomial model, right? Ideally, we think that s is equal to 1/2 at squared, right? So whatever the coefficient is for the t squared, right? Whatever that coefficient is going to be half of a, right? So let's just take a look at that, right? Let's look at the position graph here. Well, there it is, right? Notice that let's see if I can do this. Wait, hold on. I used to know how to do this. Oh wait, no, it's do 4. Okay, watch. Let's grab this. Okay, so there's that. That thing is 400. Oh, I can't paste into the presentation. Dang it. Okay. Anyway, 482 is, just remember that, 482. Okay. So this thing is 482. So half of A is 482. Okay. Now, what is A? Well, A is just twice that. So take that 482, multiply by 2, right? Is A. So 482 times 2. I get 964, not too bad, right? And that's centimeters per second squared, right? So according to the polynomial model, we think it's about 964. Now again, you're going to look at this, see that right there, that coefficient of x squared, because x is really t, right? So 1/2 at squared, 1/2 a is 482, right? So if that's half of a, then all of a is twice that, right? Okay, so that's the polynomial model. Okay, the slope of the velocity graph is easy, right? The slope of a velocity graph is the acceleration, right? So let's take a look at that velocity graph. Hey, look at that. Here it says it's 959. You see that right there? Okay, that's 959 like that, okay? So the slope is 959, so therefore the acceleration is 959 centimeters per second squared. Okay, so again, on that graph, right, that slope is the acceleration, right? So there it is, right? Okay, now from the log-log graph, this is a little bit obscure, right? Okay, so if s is equal to 1/2 at squared, what we do is we took the natural log of this, so we have ln s, right, is equal to, well, it's basically these two are multiplied together, right? So it's going to be ln 1/2 a plus, well, the natural log of t squared is 2 ln t, right? Okay, so there's a cool thing with a log-log graph. The slope of that graph should be the exponent. We should have a slope of about 2. So let's see what we've got. Let's look at the log-log graph. Well, we got 1.9. That's okay. Not quite 2, right? We're also not getting 9.81, so that's not a huge surprise, right? So that slope right there should be the exponent. We think it should be 2, right? But it's not, right? This is just like logarithm stuff, right? But here's the cool thing is that the y-intercept is the natural log of 1/2 a, right? So if we go e to the y-intercept, right? What's our y-intercept? Our y-intercept is 6.03, right? So e to the 6.03, that should be 1/2 a. And this one's, by the way off, okay? So let's do it anyway. Okay, so if I go I go second e to the whatever, and I go 6.03, I get 415.71. You can see we're going to be way off here, right? So therefore, a is just 2 times this, right? So that times 2 is, and I'm getting 831. That's way off. That's okay. Just sometimes that's just the way it is, But that's what I get from this data, from the log graph. And it could be that we're not getting very many sig figs here. It could be something else that I'm just not thinking of, okay? All right, and then finally from the linearization graph, right? We graphed, so S is 1/2 AT squared. If you graph S versus T squared, the slope of that graph is just 1/2 A. That's the slope. Okay, literally if you make T squared the x-axis and S the y-axis, the slope's going to be 1/2 A. So let's take a look at that, the linearization. There it is, 474. That's 1/2 A. Remember, 474. Okay, so 474. That's the slope is 1/2 A. So therefore, A is twice 474. 474 times 2. That's a little closer, right? A, I get 948 centimeters per second squared. Okay. So what I want you to do for this part is just show these calculations. Show this. Show this, show this, show this, and then write a sentence. Here's the sentence. From the polynomial model, I get an acceleration of 964 centimeters per second square. The slope of the velocity graph is 959 centimeters per second square. The log graph is an outlier at 831 centimeters per second squared. And the linearization graph is in the ballpark at 948 centimeters per second squared. However, none of these are what we think it should be, which is 981 centimeters per second squared, and that could be because of friction or something like that. Just that's what you want to write, okay? Let's just do a little writing there. But anyway, that's how to answer that question.